Okay, back to where we ended off there. I got interrupted by the internet. So imagine that we're trying to predict, right, how much somebody based on this linear regression is going to save if they save up for 9 weeks. So I'm going to take that number of weeks there, which is going to be 9 weeks. I plug that into my regression analysis formula, and that gives me a y value, a dependent value of 3,167 and 50 cents. So essentially, I'm using that straight line regression relationship to predict based on 9 weeks of saving. That person is going to save 3,167 and 50 cents. So again, regression analysis is using the idea of the linear relationship between our x variable and our y variable, defined both by the slope, our b1, and our y-intercept. So the r squared, the coefficient of determination, is a little different. It doesn't have any negative values because it's squared, but again, it tells us the amount of variance that the independent variable x can predict based of the dependent variable y. So for example, and the r squared goes from 0 to 1. 0 being that there's no predictive power, 1 is that there's perfect predictive power. So if you get an r squared equal to 0.49, that means that your regression formula is able to explain 49% of the variation of the dependent variable, i.e. the y variable. So we both use simple r squared and something called multiple r squared when we have more than one independent variable in our regression analysis. So just going over some of the assumptions that we have with regression analysis. We want our dependent variable, our y variable, to be normally distributed. Ideally, our independent variable should be normally distributed too, but this is not super essential. Something called multicollinearity is not wanted. Basically, we do not want a lot of overlap or association between our predictive variables, our x variables. And related to that, we want our observations that we're collecting to create our multiple regression model to be independent of one another. So each of them is a good predictor of the dependent variable. So we can use regression analysis, right, to see where the model actually is doing poorly in predicting a certain variable. So basically this regression analysis on the right here is predicting a certain variable over these polygons on the left here. So you can analyze your regression analysis and see where you have outliers, right? And those outliers can tell you that in those certain regions, you're likely missing an important variable to predict. So that can allow you to go back and maybe add another variable that allow you to predict better in those certain couple areas. So let's look at an example here of regression analysis where we're on the slide here, we're looking at 381 census tracts where we're comparing median house value on the X, median income on the Y. So you can see our regression analysis gives us, there's a positive relation in terms of correlation, right? So based on this regression analysis here, right, for a value of 70, right, we're going to get a predictive value of 30, while the actual value from the observations was only 22, right? So you can see as we get more residuals, meaning more spread of the dots or the points away from the line, more uncertainty is going to be in our model, and we're going to have a lower coefficient of determination. So if we're just dealing with bivariate regression, where we just have one x value predicting a y value, right, we're going to use a simple r squared. When we start to put more than one independent x value in, that's going to tend to increase our r squared values. But as we increase the amount of x independent variables that we're putting into our model, we also have to deal with something called the adjusted r squared, which basically penalizes the model for adding in more and more independent variables. So the coefficient of correlation, r, and the coefficient of determination, r squared, are mathematically related, right? So in this case here, we looked at the scatter plot. If we take our r coefficient of correlation and square that, we get our coefficient of determination r squared. So with regression output, we can do a stat test to see whether a certain input variable is a significant predictor of the dependent variable. So the null hypothesis in this case is that each independent variable is not a significant predictor of y, or the dependent variable. And it's only when we reject this null hypothesis is that we're going to say that yes, that particular x independent variable is a significant predictor of the dependent variable. So we can set this up in like a classical stat test where we're looking at the p-value. If the p-value is below a certain alpha value, or that predictor value, we can reject the null hypothesis and say that it is a significant predictor of y. So another function, like I mentioned before, of regression is that it allows us to control variables, right? So imagine I have a dependent variable y, which is plant height, and I'm trying to predict the value or how high a plant's going to grow based on 5 different independent variables, right? So one variable is light color, and then we have water, soil, temperature, and how much daytime and nighttime they get. So if I set up a multiple regression analysis with all these 5 independent variables, and I just want to see what the effect of light color is going to have to see if it's a significant predictor or not, I can hold in my regression analysis mathematical equation all of these other variables constant to see how much difference I'm going to have in plant height just based on changing the variable of light color. So you can do regression analysis in Excel, again, under the data analysis function in the data tab. So here's an example here of a very simple data set with 3 pairs, 3 x values and 3 associated y values, and I plotted them up in a scatter plot there. So I draw a line through it. You can set your line to whatever shape you want. I'm going to go with linear, and you can go down to set the equation and the r squared, your coefficient of determination. So there, right there, is my simple multiple regression model predicting the y variable from the x variable. So I can, if I change my data set, I can see that dramatically reduces my r squared. So now it's a very much poorer predictor of y. So again, just to show you how to go through it here, go to the data analysis. You can look at under the options there, there's regression. I'm going to go hit OK for regression. I'm going to input my x variables and input my y variables. Include my labels, confidence level 95%, and then I'm going to output set where I'm going to put the results. Hit OK, and there's the outputs of my regression analysis. I'm just going to stretch things out here, see things better. So you can see there, regression stats, I have my multiple r, my r squared, my adjusted square r squared. So in this particular case, right, I have a r squared, a coefficient of determination of 0.9918, a very high r squared. But is that significant or not statistically? Well, I can look at the p-value. So I can see here, I have a p-value of close to 0.06. So at an alpha level of 0.05, I would actually reject that x is a significant predictor of y. Now let's expand my sample size. Instead of 3 values, let's have 18 values. So again, I'm going to go into my regression analysis in Excel, put in the data values for x and y. So again, you can see I have a very strong r squared, similar to the previous example with 3 data points. Now you can see I have a much lower p-value, right? E to the minus 29, which is essentially 0. So you can see that even though I have the same, basically the same r squared, because I have a greater sample size, now I have a significant predictor of X being a significant predictor of Y. So let's do a couple more examples here, which you can find in the Excel spreadsheet. So here we have data where we have the dependent Y variable, what we're trying to predict being household price. And then the two variables that we're going to use to predict household price is the square footage, the size of the house, and how far it is from school. There's our two variables, right? So we do the regression analysis, we'll see that square footage has a positive relation to house price, which makes sense. The bigger the house, on average, tends to be increase the house price. And then we have a negative relationship between house price and distance to school, which makes sense because people usually want their houses, everything else being equal, closer to the school. So if we plot these two variables up independently, we can see that we have a relatively weak relationship between the size of the house and house price, positive relationship, more stronger and negative relationship between distance to school and house price. So if we do run the regression analysis, we get our coefficients there. So you can see that is basically our beta value that we're going to multiply our X value by. So it's plus value, 123.06. Distance from school has a negative sign in front of it, right? Indicating that there's an inverse relationship between distance from the school, right, to the house price. But let's look at whether either of these is a significant predictor of house price. So that's where we get our p-value. So in this case, we see that both have relatively small p-values, well below 0.05, if you use that for an alpha value. So in this case, both of these inputs, square footage and distance to school, would be significant predictors of house price. Do another example here. This time we're trying to figure out if we can predict the amount of total movie sales in millions of dollars, now based on three input variables. Movie production cost, how much it took to create the movie, advertising budget, and book sales. So let's first look at a regression analysis, using only one input variable and see how that changes the R squared. So let's first look at the variable of movie production. So I'm going to put movie production. So I'm going to be trying to use just the variable of movie production to predict total movie sales. And what are my results? Well, I get a coefficient of determination of 0.14. So that's telling me that this one variable only predicts 14% of the variance of total movie sales. So not a very good, very strong predictor. So, and also have a very high p-value, indicating that it's not a significant predictor of total movie sales. So let's add in another variable. This time we're going to put in also the advertising budget variable X2. So now when we add in the advertising budget, we see that we increase our R squared considerably, going from 0.14 up to 0.86. There we have our adjusted R squared, which comes into play when we start to put more than one independent variable into our regression model. So we have an adjusted R squared of 0.825. Now let's add in the third independent variable to see what happens to our R squared and our adjusted R squared. So not much happened to the adjusted R squared when we put in book sales, the third variable, but you can see that our adjusted R squared did go down. So again, the adjusted R squared is kind of like, you can think of it as kind of penalizing the model for just adding in variables which are not significant predictors. Because down here, we can see that for book sales, it has a very high p-value. So it's not a significant predictor of total movie sales. Okay, let's do another example here. So in this example, our dependent variable Y is going to be the number of cars in which a household has. And two independent variables, one's going to be the number of people in that household. The second one is going to be the annual total income within that household itself. So the first thing we can do a scatter plot between both of those variables. So we can see in this case, we have a positive relationship between both the people in the household and the income versus how many cars are found at that household. If we run the regression analysis tool in Excel, there we get our p-values. So we can see that the variable of people in the household is a significant predictor of the number of cars that'll be in that household, but the total annual income in this case is not a significant income or indicator predictor based on its very high p-value. Okay, so that ends the second video for correlation and regression. So this will be what we'll be doing in the next lab. So have a good weekend, and I will see you on Tuesday.